Morning class. In the previous lecture, we were discussing structure of solids, and in that we have already discussed the important structures of ionic solids. In today's class, we will going to discuss two important structures that is being formed with covalent bonds. So the structures are popularly known as the covalent structures, and the corresponding solids are referred as the covalent solids. So as the name suggests, in this particular portion we are going to discuss the structure of those materials which is primarily being made with covalent bonds. And we know covalent bond forms by sharing of electron, and the sharing has to take place between neighboring atoms. This results into the formation of directional bond, and generally the covalent bonds are much stronger as compared to other kind of bonds. So the structure that we will going to refer here are the ones which have stronger mechanical properties, but they also have directionality, and because of the directionality they exhibit anisotropic properties. That means in different directions the same material exhibits different properties. So the first important crystal structure which many covalent solid forms is called the diamond cubic structure. If you can remember, when we were studying the structural analysis through X-ray diffraction, we have referred the rules for the diamond cubic structure also. At that time, I have told that it is a variant of the FCC structure, and the exact structure we will study it later. So in today's class, we will going to understand the diamond cubic structure. As the name suggests, diamond cubic structure represents the structure of a diamond, and diamond is a solid that is primarily being made of carbon. So the structure that we are referring, its primary variant is the one that is made up of carbon, and we know the carbon structure or the diamond cubic structure since our primary school days. This is a variant of an FCC structure. You can clearly see in the schematic diagram. If you focus only on the yellow color balls, the yellow color balls represents the FCC structure. And apart from the yellow color balls, you also have 4 gray color balls. And if you closely look at the position of these 4 balls, which is in the gray color, you can clearly see their positions is actually the tetrahedral sites. So diamond cubic is basically the structure which is the cubic lattice, or more precisely the face-centered cubic lattice, with out of the 8 tetrahedral sites, 4 of them are occupied. Now remember, the atom sitting at the tetrahedral site could be same as the lattice atom, because in the diamond all atoms are carbon. So the atom occupying the tetrahedral site and the atom occupying the regular corner or the face centered sites are same. In many other solids which forms the same crystal structure may have the lattice atom and the atom occupying the tetrahedral site are different. So I will quote couple of more examples where the atoms at 2 different sites are different. Generally in diamond cubic structure, if the carbon is occupying the tetrahedral site, then it is in the sp3 hybridized state. You remember the organic chemistry that we have learned in +1, +2. We know that carbon can form bond with its neighboring carbon, either a single bond, a double bond, or a triple bond. And under different circumstances, the orbitals of carbon superimpose on the orbitals of neighboring carbon in a way that it creates a hybridized structure. So you can have an sp hybridization where an s orbital overlaps on the p orbital, or you can have an sp2 hybridization where one s orbital overlaps with two p orbitals, or you can have an sp3 hybridization where one s orbital overlaps on three p orbitals. So in the diamond cubic structure, every carbon is in the sp3 hybridized state, and that also means that we have carbons bonded with its surrounding with 4 carbon atoms. So primarily the nature of bonding in the diamond cubic material is the sp3 hybridized structure, right? Later on, we will discuss another variant of a carbon structure, which is called graphite, and graphite will have a different kind of hybridization in it. So what is diamond cubic structure? Diamond cubic structure is basically the FCC lattice with, out of the 4 tetrahedral site, 4 is being occupied by an atom. If it is diamond, then the atom occupying the tetrahedral site and the lattice site are the same carbon atom. And if it is some other material, then the lattice atom and the atom sitting at the tetrahedral sites might be different. So what are the motif positions? As I said, we have 2 different type of atoms, one sitting at the lattice position and the other one sitting at the tetrahedral positions. We have discussed this previously. Whenever you have atom occupying the lattice positions, we refer its motif to be at 0, 0, 0 site, because 0, 0, 0 site means atom is sitting at the lattice point. And the other type of atom is at the tetrahedral site. So with reference to the lattice site, the tetrahedral site is at 1 by 4, 1 by 4, 1 by 4. So your motif coordinates are 0, 0, 0 or 1 by 4, 1 by 4, 1 by 4. Out of the total available tetrahedral site, only half of them is occupied. We know in a unit cell we have 8 tetrahedral site, and in the diamond cubic structure only 4 of them is occupied, so our occupancy is 50%. In case of compounds, like diamond is a monoatomic structure, only one type of atom is making the solid. But in many other cases where 2 atoms participate to form the solid, you end up with a compound. And in those cases, FCC lattice can be formed by one type of atom, and the other type of atom, usually from the same group, means from the same group in the periodic table, goes and occupy the half of the tetrahedral site. For example, if you have a semiconductor like gallium arsenide, if you have a semiconductor like gallium arsenide, then gallium goes and occupy the lattice site, while arsenic, being a smaller atom, goes and occupy the tetrahedral site. Remember, whenever the compound is being formed, the larger atom will always go and sit at the lattice site, while the smaller atom will always go and occupy the tetrahedral site. In diamond cubic structure, always out of the 8 tetrahedral site, only 4 will be occupied. And what is its position? Its position is always an alternate position. So how can I show that? To understand that, focus on the unit cell and look at the first tetrahedral site which I have circled. Now, if you go parallel to this on the back face, you will see that that particular position is empty. So if I go on the back side, you will see that tetrahedral site is empty. Likewise, if I move on the right hand side, the right hand side tetrahedral site is also empty. So if one of the tetrahedral site is occupied, surrounding it, the other one will be empty. So on the front face, on the right hand side, where my cursor is there at this position, you have an empty tetrahedral site. And now if I go backward from that point, you will see there is an occupied tetrahedral site. Now if I go from this side on the top, you will see there is an empty tetrahedral site. And if I go on the, we are on the back face, and now I am moving to the left face, you see it is occupied. So out of the four, always the alternate two is occupied in every direction. Okay, there is a question from Siddharth. He is asking how motif is calculated if we have been given a unit cell. Okay, motif is basically the position of an atom vis-a-vis to the lattice point. So if the unit cell is given, from the diagram you can see the position of the atoms. The positions of the atom is at the lattice site, then your motif coordinates are always 0, 0, 0. If it is occupying either the tetrahedral void or the octahedral void, then depending on the nature of void, your motif coordinates may be 1 by 4, 1 by 4, 1 by 4 for the tetrahedral void, and 1/2, 0, 0 for the octahedral site that sits at the edge center, or 1/2, 1/2, 1/2 for the octahedral void that sits at the body center. So these are the three motif coordinates that you can possibly have. Is it clear? Okay, let's proceed further. So let's calculate the APF for the diamond cubic structure. If you remember, we have defined the APF for the simple cubic, face-centered cubic, and body-centered cubic unit cells. APF is being defined as the ratio of number of atoms in the unit cell to the volume of one atom divided by volume of the unit cell. So it is basically the ratio of atoms occupying the unit cell to the total volume of the unit cell. So let's do this exercise. How many atoms we have in the unit cell? If you look the unit cell, you can clearly see there are 4 atoms occupying the tetrahedral site. They are completely within the unit cell. So they contribute 100% to the unit cell, while the corner atoms and face-centered atoms are shared between the neighboring unit cells. So you have to consider their effective contribution to the unit cell. And we know the corner atoms contribute 1 by 8 and the face atom contributes 1 by 2. And like that, if you compute, the total contribution from the lattice positions is equal to 4, and other 4 is coming from the tetrahedral side. So we have total number of atoms in the diamond cubic unit cell is equal to 8. So we have 8 atoms. So if I write APF, I have number of atoms which is equal to 8 multiply by volume of a single atom which is equal to 4 by 3 pi r cube. So we have 8 into 4 by 3 pi r cube divided by volume of the unit cell which is A cube. Now, if you remember, whenever you are deriving the APF, we convert R in terms of the lattice parameter A. So for that, what one should do is one should look along the direction which has the highest density of atoms. So if I go back and show you the unit cell, you can clearly see that the direction with highest density is the one that is along its body diagonal, because along the body diagonal you have highest number of atoms occupying its position. So we know the length of the body diagonal, which I have just shown here, is equal to root 3a. So that root 3a, and the first lattice position from the corner lattice point position to the tetrahedral void is 1/4 of the total length of the body diagonal. Say, let me show that here. If we refer this total length is root 3a, and the length from this point to this point is 1/4 of the total length. So let's consider this much length. That particular length will be equal to root 3a by 4. So root 3a by 4 is equal to, you have an atom at the tetrahedral side and another atom at the corner. So it is r plus r. So root 3a by 4 is equal to twice r. So you can, from this expression, rewrite in terms of r, which will come out to be under root 3a divided by 8. Because if you move the 2 on the other side at the denominator, 4 into 2 will become 8. So we have substituted for r in terms of a, and that comes out to be under root 3a by 8. So if I substitute this and simplify this, it comes out to be 0.34. That means APF of a diamond cubic structure is much lower as compared to the FCC unit cell. You remember, FCC has the highest packing density of 0.74. As compared to that, the APF of diamond cubic structure is only 0.34, or you can say 34%. Why this is like this? It is because your diamond cubic structure is quite porous, or you can say it is more open. It has very large amount of voids present within its unit cell. Okay, let's move to the second type of covalent structure. This one we have understood again from our primary school days. The structure is popularly known as the graphite structure. We know carbon has two allotropic forms. One is called diamond, whose structure we have just understood, and the other variant of the carbon is being referred as the graphite structure, and the schematic diagram of the graphite structure is shown here. You can clearly see from the unit cell diagram, if you closely look here, you can see the graphite forms a unit cell which is having its structure which is hexagonal. So when I say the graphite structure, it is nothing but the hexagonal structure. So everything that we talk about the hexagonal structure, same is applicable for the graphite structure. The other primary difference between the carbon making the diamond cubic structure and the carbon making the graphite structure is, in the graphitic structure, your carbon is in sp2 hybridized state. That means one s orbital is bonded with two p orbitals in the neighboring atom. That means every carbon atom is making three bonds, which you can clearly see in the unit cell. If you focus here, you can see that the carbon has surrounding three other carbon atoms. So they are sp2 hybridized. Every bond within the ring of the hexagon is bonded by covalent bond. So if you focus only on one particular basal ring you understand, right? Say, let me mark it. This particular ring is your basal ring. And you see there are carbon-carbon bonds. Each of these bond is sp2 hybridized covalent bond. So it's a very strong bond and it is difficult to break this bond. And that is why the melting point and the boiling point of covalent solids are much higher. Now, graphite has a very peculiar structure. If you look into the basal plane, your bonds are strong covalent sp2 hybridized bond. But if you talk about the bonds present between the layers of hexagonal rings, that is the vertical bond, then that bond is basically a secondary bond and very, very weak. So the bond from this atom to this atom is basically the van der Waals bond, or you can say the secondary bond. And because of that, graphite has a peculiar characteristic that the one layer of a graphite can slip over the other layer of the graphite, and because of that we have been taught that you can use graphite for lubricating purpose. Why? Because of the presence of van der Waals bonds between two layers of graphite. This weaker bond allows them to slip over each other, and that makes the graphite structure quite different from the structure of diamond, which is very, very strongly bonded, and all bonds were sp3 hybridized covalent bonds. Any doubt up to this point? The structural difference between the graphite structure and the diamond cubic structure? Okay, if there are no doubts, we are at the end of structure of solids. So with this, we are completing our this particular unit. If you remember, when we begin this course, I have told you that your first unit is very, very important from the perspective of understanding the fundamental concept. And that is why we took a lot of time in completing our unit number 1. We talk about the principles and concepts in quite depth. Now, the remaining units are the applied units. So we will apply our previous understanding, the fundamental understanding that we have acquired about solids, to understand the properties and applications of the various solids in different fields. So subsequent units we will cover to a rapid pace as compared to the time that we have devoted in this particular unit. So let's move to the another unit. Okay, the question is, what is the syllabus for MST? The syllabus for MST is unit number 1. So whatever we have studied is basically the syllabus for the MST. Yes, everything that I am teaching online, I will upload on the Google link, and I will share it within couple of days. So now we are moving to the unit number 5 of our syllabus. What about unit number 2, 3, 4? We will cover it at a later stage. This is the sequence that we are following. This is a relatively smaller unit, and we will quickly complete this particular unit within this particular week. So the unit is on corrosion of materials, and when I say corrosion of materials, our primary focus is on corrosion of metals. Why we are primarily focusing on metals? Because metals are the basic building blocks in most of the engineering and technological applications. So understanding the corrosive characteristic of material is very, very important. Remember, in most of the industrial environment, corrosion defines the life of the product. So understanding the circumstances leading to the corrosion in solid will eventually help us in designing materials which is suited for a given industrial application, so that the performance of the material do not degrade over its lifespan. So let us try to understand what exactly the phenomena of corrosion is. Remember, whenever I refer corrosion, I am referring corrosion in metals. So if somebody asks me technically what exactly the corrosion is, my answer is corrosion is nothing but an electrochemical reaction. So we have studied in our chemistry course the electrochemical reactions. These are the reactions where exchange of electrons takes place. So corrosion in metals is basically the outcome or result of an unwanted electron transfer between the species of the solid. So if you want to understand corrosion, what you need to understand is an electrochemical reaction. In chemistry, we used to define the electrochemical reaction as a reaction in which the transfer of electron takes place from one chemical species to the other. Generally, the other chemical species is the neighboring species. Metal atoms characteristically lose or give up electrons in what is called an oxidation reaction. We know metal have excess electrons in their outermost orbit, which is very loosely bound to its parent nucleus, and that is why metal atoms has tendency to give up the electrons from their outermost orbit. While doing so, they complete their outermost orbit, and we know if atom is in a state where its outermost orbit is completely filled, it is energetically more favorable state, and that is why all metals liberate their electrons from the outermost orbit, and in this way they attain higher stability on energy scale. For example, if I have sodium atom, you know sodium has the atomic number 9, so its electronic structure will be 281. So in the outermost orbit of sodium, we have one electron, and if sodium can somehow liberate that one electron, in the process sodium gets converted in from Na to Na plus, then Na plus is more stable as compared to Na. The process in which a metal liberates an electron from its outermost orbit is called the oxidation reaction. So generally, metals have tendency to undergo an oxidation. In this case, when the metal oxidizes, generally metal gets converted into metal ions with a positive polarity, and it liberates certain number of electrons to its surrounding. So an outcome of any oxidation reaction is you end up with a positively charged ion and an ion with liberation of couple of number of free electrons. The typical examples are, let us say you have an iron, then iron has tendency to liberate 2 electrons and gets converted into ferrous ion. So Fe gets converted into Fe2 plus, or an aluminium gets converted into Al3 plus with a liberation of 3 electrons. So depending on the valency, the material has different oxidation states. Is it clear? Okay, let's proceed further.
Yes.
Now, generally, in the electrochemical reaction, if one of the metal species undergoes an oxidation reaction, that means gets converted into positive anion with a liberation of electron, then some other atomic species has to absorb those liberated free electrons. In a way, it undergoes a reduction reaction. So the atomic species which accepts the free electrons from its surrounding undergoes a reduction reaction. Generally, the atoms which is already in an anionic state, that is in a positive valence state, can accept the negatively charged incoming electron, and in the process they form neutral atom. For example, if I have an H plus ion, then an H plus ion can accept the 2 electrons liberated in the previous expression by iron. Then these 2 H plus, when reacts with 2 incoming electron, gets converted into one molecule of hydrogen. You remember, H2 is a hydrogen molecule. Likewise, in the presence of oxygen, 4H plus anion can accept 4 electron, and in the process it produces 2 molecules of the water. So both these examples represents the reduction reaction of the hydrogen anion. Likewise, we can also have another possibility where a dissolved oxygen. What is dissolved oxygen? An oxygen inside the water. So chemically it is being written as O2 plus 2H2O. So a dissolved oxygen in the aqueous medium, when undergoes a reduction, that is, it accepts an incoming electron, it gets converted into hydroxide. So you can have the reduction reaction in the first case with an H plus ion, and the strength of H plus ion also represents the strength of the acidic solution. So your first reaction is under acidic condition. The second one is also involving H plus ion, so it is also under acidic solution. And the last one ends up in the production of OH minus ion, so it is basically in the basic condition, right? So your reduction reaction can take place into an acidic environment or into a basic environment. So overall, if somebody asks what is electrochemical reaction, your answer would be an electrochemical reaction is nothing but an oxidation reduction reaction where a metal species undergo an oxidation reaction and a surrounding H plus ion will undergo a reduction reaction in the acidic condition or in the basic condition. Now, generally, to see the strength of an electrochemical reaction, you need to measure a quantity which is called an electrode potential. So how do I know the electrode potential of a metal? To measure that, what you need to do is you need to construct a standard half cell. So what exactly the standard half cell is? The standard half cell is shown in the schematic diagram with the encircled region in a dotted green line. What you have is a metal electrode. Metal electrode is nothing but a sheet of a metal which is being kept in the solution of the same ions. So for example, in this particular case, we have the metal sheet which is made up of copper. So we have sheet that is made up of copper. Then the solution that we are using is also the solution of copper ion. So we have 1 molar solution of Cu2 plus ions. So if I have a metal plate which is dipped in a electrochemical solution of the same ions of 1 molar strength, the resultant structure is called the half cell, standard half cell. Likewise, we have also constructed another half cell with the iron plate. So we have an iron plate here, and then we have solution, an electrochemical solution of Fe2 plus ions with a 1 molar strength. Once you have these two halves standard cells ready, we divide them through a membrane. Membrane is basically a porous medium which prevents the mixing of these two solutions. So you have a membrane present here in between these two standard cells, and then two metal sheets are connected electrically through the voltmeter. So we have a voltmeter that is electrically connected on either side with two metal plates. So whenever you construct an electrochemical cell like this, which is actually made up of two standard half cells, you will see your voltmeter will going to give us some non-zero voltage. Why there is a non-zero voltage? This is because there is a net flow of charge from one metal plate to the other metal plate, depending on the direction of flow of current. You may have a positive voltage or a negative voltage, and the voltage that is being measured in the couple of two metal species is being referred as the electrode potential. For example, For the standard shell, which is shown in this particular schematic diagram, that is made up of iron and copper, we know the copper, which is Cu2 plus, has tendency to accept the two incoming electrons, and it results into a neutral copper. So Cu2 plus, when reacts with two incoming electrons, it results into Cu0. So what happens? The Cu2 atoms in the electrochemical solution here accepts that two incoming electrons, gets converted into neutral copper, and that neutral copper goes and get deposited from the solution onto the metal plate. So you have an electrode deposition of copper that is happening on half shell where there is copper plate. Contradictory to this, at the iron side, iron from the plate liberates two electron and gets converted into Fe2 plus. That means iron undergoes an oxidation reaction, because liberation of electron is your oxidation reaction. So Fe gets converted into Fe2 plus with liberation of two electrons. And what happens in the half shell where there is iron? So Fe from the metal sheet gets oxidized and goes into the solution. So you have ions coming from the sheet into the solution, and in a way they transfer from the two electrons that is being liberated is being transferred from external circuit from iron to the copper. So the electrons will go from iron sheet to the copper sheet through an external circuit, and in this process it generates some voltage. The measured voltage in this case is 0.78. That means the electrode potential between the junction of iron and copper is equal to 0.78 volt. Remember, this voltage depends on the nature of the material. So instead of iron or copper, if I have another pair of metals, your electrode potential will be different. And at a later stage, I will explain if this number is different, what is its significance. So what we understood up to this point is copper has tendency to accept electron and gets converted into a neutral copper atom. That means copper undergoes a reduction reaction. And iron has a tendency to liberate electrons. That means iron undergoes an oxidation reaction. So whenever two dissimilar metals are in contact with each other by electrical means an electrical cable is interconnecting the two metals, one of the metal will undergo an oxidation reaction and the other one undergoes a reduction reaction. The strength of the reaction is being measured in terms of its electrode potential, which is displayed here as 0.78 volt. Remember, in technical terms, the junction where material undergoes an oxidation reaction is referred as anode, and the junction where the material undergoes a reduction reaction is being referred as the cathode. So for us, copper side is the cathode side and iron side is the anode side. Okay, I think we are running out of time. So let's stop at this point and we will continue to have our discussion from this point onward in our tomorrow's class. If you have any queries, keep it for tomorrow.